Hello all, my name is Sergio García and I am a PhD student at the Complutense University of Madrid. My talk is going to be about the measurement and prediction of galaxy assembly bias across galaxy samples, as was presented in the paper that Jonas and I submitted in April. Before diving into the contents of this paper, I'm going to introduce a couple of theoretical concepts that are very important to be understood. The first one is the halo assembly bias, which is the dependence of halo clustering on halo properties beyond halo mass. This assembly bias shows no dependence on redshift, as was demonstrated by Gao et al. In 2005. Therefore, we can combine results from different redshifts in order to reduce statistical noise. This will be especially useful once we try to model halo assembly bias with the objective of predicting galaxy assembly bias. In this work, we have analyzed three different halo properties: concentration, spin, and cosmological formation time. The second concept I want to introduce is the occupancy variation, which is defined as the dependence of the galaxy content of halos on secondary properties beyond halo mass. This means that galaxies, instead of randomly populating halos independently of any property different than halo mass, may prefer to populate halos with a higher or lower values of any given property relative to the entire sample of halos. As an example, we can see to the right the figure showing occupancy variation depending on concentration. This plot will be explained in detail later. Empirical models traditionally assume that halo mass determines galaxy content. However, recent studies have demonstrated that second-order effects do indeed exist. For example, galaxy assembly bias is one of them. Galaxy assembly bias is the dependence of galaxy clustering on halo properties beyond halo mass, and arises from the interplay of halo assembly bias and occupancy variation. This means that halo assembly bias is a prerequisite for galaxy assembly bias. Even if all galaxies prefer to populate halos with higher values of a given property, if there is no halo assembly bias due to that halo property, then there will be no galaxy assembly bias. Likewise, if galaxies randomly populate halos independently of any given property, then the halo assembly bias signal of halos with higher values of that property may cancel out with that of the halos with lower values of the property. To measure the total galaxy assembly bias present in any given galaxy sample, we must first shuffle the galaxies between the halos of similar mass. Then we compute the two-point correlation function of both the original and the shuffled versions of the sample and take the ratio between these two functions, obtaining the data points of the figure to the right. Due to the stochastic nature of the shuffling process, we need to shuffle the galaxies a total of 100 times in order to produce reasonable results. Also, taking the median of the 100 different results above 8 megaparsecs, we obtain a total of 100 galaxy assembly bias measurements, which, taking the mean, gives us this horizontal line representing the total galaxy assembly bias present in the sample. Then, if we want to measure the galaxy assembly bias captured by a given property, we must repeat the shuffling process, fixing not only halo mass, but halo mass and a secondary halo property. For example, concentration, spin, and formation time. in a similar fashion, we obtain these horizontal lines representing the galaxy assembly bias captured by its halo property. If the bias captured by a given property were equal to a total bias present in the sample, then these measurements would follow the original sample measurement. Following this procedure, we have measured the galaxy assembly bias present in 53 different galaxy samples from the IllustrisTNG 300 simulation. These galaxy samples have different sample criteria represented by the rows in the figure to the right, different redshifts in the horizontal axis of each individual panel, and different number densities in the columns of the figure. The vertical axis of each individual panel corresponds to equivalent figures like this, and each data point corresponds to the horizontal lines of the galaxy assembly bias measurements. From this figure, we can learn two main things. The first one, that concentration, spin, and formation time don't fully explain the galaxy assembly bias in any of the samples analyzed in this work. We can also see that galaxy assembly bias depends upon the galaxy sample that we are looking at, changing clustering by as much as 25%, as we can see in this panel here. Then, to model halo assembly bias, we will use a sigmoid curve with the expression showed up here. And to measure this halo assembly bias, we will compute the ratio of the clustering of halo subsamples, namely with 30% of the halos with highest and lowest values of concentration, spin, and formation time, and take the ratio of the clustering to that of the entire sample, obtaining these figures where the horizontal axis is the peak height of the halos, which is a variable that combines halo mass and redshift in a single variable. Then, to model occupancy variation, we will use the ratio between the median value of the target halo property for halos with and without galaxies. Here I'm going to highlight the blue galaxy sample, where galaxies prefer to populate halos with lower values of the concentration. That, combined with the lowest value of the concentration halo assembly bias curve, is hinting us at a negative galaxy assembly bias. Then, if we look at the corresponding galaxy assembly bias measurement panel, we can see that that is indeed what happens. Once we have modeled both halo assembly bias and occupancy variation, we can proceed to predict galaxy assembly bias. To do that, we will first express the linear bias of any given galaxy sample with this expression. Here we have an integral over halo mass of the linear bias of a halo with that mass, weighted by the number of galaxies inside halos with that mass. This is then normalized by the total number of galaxies inside the sample. However, this expression does not take into account halo assembly bias. To do that, we need to add here a term of the form of 1 plus the halo assembly bias fraction, which is ranged between -1 and 1. Then, taking the ratio of the linear bias which utilizes halo assembly bias and that which doesn't, we can obtain a galaxy assembly bias prediction that, when plotted against the galaxy assembly bias measurements, correlates with the measurements with a Pearson correlation coefficient of 0.8. To summarize this talk, we have seen that galaxy assembly bias strongly depends upon the number density, redshift, and sample criteria of the galaxy sample we are looking at, capable of changing a galaxy clustering by as much as 25%. We have also seen that galaxy assembly bias arisen from concentration, spin, and formation time don't fully explain the galaxy assembly bias present in any of the galaxy samples that we analyzed. This means that empirical models that only utilize one of these properties cannot reproduce the predictions from hydrodynamical simulations. We have also seen that the galaxy assembly bias estimator that we propose reproduces predictions from hydrodynamical simulations with a correlation coefficient of 0.8. One could incorporate galaxy assembly bias into a halo model using this estimator, like in any particular hydrodynamical simulation. I hope that this talk has been interesting for you, and I'm available to answer your questions.